All right, everybody, welcome to lecture 6. We're really excited for everybody to be here, and we've got some really cool stuff that we're going to be talking about this lecture. So let's get started.
Okay. Okay, we're going to first start off with talking about some announcements. The first of which is that we're doing a little bit of an extension on the iPoduino. So a lot of people have been struggling with this project, or maybe just as a quarter, this quarter as a whole. And we have a sort of low finish rate. So yeah, instead of assigning a new project, we decided we would give people a little bit more time to work on it. So if you're one of the people who hasn't finished yet, or yeah, just are behind, we really urge you guys to use this extra time to finish it and get caught up. Yeah, and also for those who have finished, we are thinking about doing an optional project for you to do if you want to do something more with the time. Yeah, some more information will come on that in coming weeks. Okay, and next we have.
So we do have a couple of really cool events that IEEE is hosting for this 3-day weekend. The first one is a movie night. It's going to be in the Tesla room at 8 p.m. tonight. So feel free to stop on by if you guys want to just decompress before a really long weekend and a really rather long week, if I'm being honest. All right, next slide. We're also going to be hosting a Frisbee tournament. We've got a lot of really good Frisbee players on the officer board. It's also just a really great way to get active. It's going to be at 7 p.m. at Drake Stadium tomorrow on Friday. And then the last event is on Monday. This is a personal favorite of mine. We're going to be going to Cliffs of Vid in Culver City on Monday at 10. It's a really great way to meet fellow IEEE members and also get out of Westwood. Definitely RSVP by tomorrow night. The hyperlink is there. Yeah, my bad. The date's wrong there. But yeah, it's going to be on Monday, but RSVP by tomorrow night.
Okay, awesome. And then finally, just something that we want you guys to start thinking about is that IEEE Officer Board applications are actually coming up surprisingly fast. They happen really early in spring next quarter. So start thinking about what position you guys might want to run for. Being on the IEEE Officer Board is so much fun and just a really great experience. So we really recommend that you guys run for a position. So yeah, start thinking about it and feel free to ask us any questions. And also, you know, we're looking for future ops leads. So yeah.
Yeah, I just wanted to add, like, reach out to us or any of the other officers if there's a position that you're interested in. We're happy to ask the officer about the position to relay it back to you as well.
Yeah. And early next quarter, we'll have an info session with more information about running for officer board that you guys should definitely go to. Okay, and with those announcements out of the way, let's review what we did last time.
Yeah, so the first question I have is, what is the difference between an analog and digital signal? You guys are more than welcome to type in the chat or unmute yourself to get the answer. Or if you don't remember, we're happy to answer it as well.
Go for it. Take your best guess. Okay, nice. Yeah, analog is like a sine wave, digital only at high or low. Yeah, so analog can have continuous values, and digital exactly has only high or low. Has just 2 set values. Nice job. Now for the next question, what is the return value of analog read? What could it return, I guess?
So the return value of analog read is actually 0 or through 1023. 0 to 255 is it's one of the arguments for digital write. Or sorry, not digital write, analog
write.
Yeah, my bad.
Yeah. So, but that's a really common mistake actually, is mixing up the two, because you both use them. It's sort of weird that they have different units, but analog read, yeah, will give you a value 0 through 1023, but when you're actually writing that same signal, you want to use analog write with 0 to 255. So a little weird, but that's what you get. Okay, and then finally, how do you hardware debounce a button? Any guesses? A capacitor.
Awesome,
Nice job, Jonathan. Yes, you use a capacitor. Okay, let's move on then. This time on ops, we are going to be covering transistors and IR sensors.
Debouncing. So debouncing is basically when you press a button, you have a bouncing of the signal, and it's not just a complete on or off, and you have some noise basically. And so debouncing is removing that noise so that your signal works properly. We talked about it in the last lecture as well, so feel free to check those slides out as well.
Yeah. Okay, awesome. So great. Let's start with transistors.
All right, so transistors are the building block of basic circuit design. This lecture, I'm going to be going a little bit more in depth than you actually need to be able to work through any of the projects in ops, but I figured it would be a great introduction into transistors and basically what hardware EE is all about, and a lot of upper division EE courses. So today we're going to be talking about its applications, what it looks like and how it works, and then how you can actually use them in circuits. So one of the most important applications of a transistor is using it in digital logic design, because transistors can be used as electrical switches. You can generate NAND gates, NOR gates, and any gate that you can think of, you can generate simply by using transistors. I have a question for the audience. Can you think of a mechanical switch that we have used already? It's okay. Buttons. Yeah, exactly, Brian. Yeah, exactly. So a button is a kind of mechanical switch. You do have to unfortunately press it, and it is quite big and clunky. So given that logic, follow-up question is, why would we want an electrical switch over a mechanical one?
Any guesses? No wrong
More
answers.
switches because it's fun. That's true, Samuel. More precise, easier. Yeah. Yeah, so these are all right answers. In addition to just being easier to use because you can automate it, electrical switches are really, really small because of transistor technology. And so you can actually put more transistors onto a board and automate more things. And the more transistors you have, actually, the more computing power you have. So you're actually like optimizing your board or your chip. And another thing is that transistors, because they're so small, they're really cost effective. So that's one of the applications, is just digital logic design. You can basically just adjust your, you can basically create any sort of gate using just applying different voltages to these A and B inputs here. And then you can move to the next slide. The second application of transistors is for amplification. Essentially, you can create a really small signal. You can input a very, very small signal and then generate a very large one. If you see here, this IB current, I know this diagram can be a little bit scary, but this IB current is that's your input, and it's generally on the magnitude of microamps, and the resulting voltage from this transistor is really large. So it's kind of like magic, like you're taking some very, very small amount of power and energy and generating something very large with it. And this is why transistors are the fundamentals of circuit design, because you're able to again, take a large signal with very little power consumption. And if you guys are at all interested in hardware design or circuit design in real world applications, I definitely recommend taking ECE 115A or 115B, because it'll give you a really good look into what actual real world applications of circuit design is. So now that we understand the really important applications of transistors, now let's look into two different types of transistors. The first is a BJT or bipolar junction transistor. A BJT is a current controlled device and it's incredibly power efficient. BJTs are one of the earlier transistors that were designed, but because of how power efficient it is, it's still commonly used today. And it's the transistor that we'll be mainly focusing on and working with in upcoming projects. The other transistor that we have is the MOSFET or metal oxide semiconductor. They are a voltage controlled device and they're more often used in logic design because they're not as power efficient as BJTs. Another really cool thing about them is that they are symmetrical, so you don't have to worry about the orientation of MOSFETs. BJTs are unfortunately not, so you do have to worry about the orientation. And that's just kind of what they look like in real life and some of the symbol diagrams. So now looking at the BJT structure, we have the collector, base, and emitter. And if you notice here, BJTs have 3 different pins, and this is completely different from any other type of component that we've worked with. Resistors, inductors, capacitors, regardless of how complicated they can be, it's nice because you only have to worry about 2 pins. But when you have the introduction of 3 pins, that's where a lot of the math gets a little bit complicated, and I'll try to break it down as simply as I can. But essentially what a BJT is just semiconductors stacked on top of each other. Now, in this left example is an NPN transistor, and an N semiconductor is basically just a semiconductor that has a lot of moving electrons that are able to move around. Meanwhile, a P semiconductor is one that has a lot of holes that can move around, and holes are just the absence of electrons. So there are just, as you can see, 2 different types of semiconductors, and they're stacked on top of each other to create this BJT. I did want to note a couple of things here. We'll talk about doping and stuff like that in the next slide, but it's important to understand that this N, the collector N semiconductor is actually lightly doped. The P semiconductor is also lightly doped, and this emitter semiconductor is highly doped. And part of the reason for that is because it actually allows for a lot of current generation to be produced. So those are a couple of things about the BJT structure itself. But before we go too in depth about how current is able to be generated, let's figure out what doping is. Doping is essentially the addition of impurities into a pure structure of silicon, generating extra holes and electrons that are free to move around. In this left example here, I have, let's say, pure silicon, which is these four silicon elements, and then you are adding an impurity such as antimony, which is the Sb symbol. And when you add antimony into silicon, you actually generate a free moving electron. And that's really important and different from, if you see the electrons that are circled around a silicon and then also antimony, those are electrons that cannot move anywhere. But when you add this additional antimony, you're generating an electron that can move everywhere, and that is what is actually able to generate current. On the flip side, we also have, let's say, the addition of boron into a pure silicon structure, and the addition of boron generates holes, which again are just the lack of an electron. And this hole is again able to move and is what's actually generating our current. So that's a little bit about doping. It's basically just adding different impurities into a silicon structure in order to generate extra holes or electrons that can move around. Okay, so now understanding the physics of it all. So when the base voltage, and remember that the base is this, the semiconductor sandwich between the other two. So when the base voltage is greater than the emitter, which is on the bottom here, and we know that because the battery voltage is positive when connected to the base and negative when connected to the emitter. When the base voltage is greater than the emitter voltage, the electrons in the N semiconductor flow towards the battery. You can think of it as opposites attract. So the electrons are attracted to the positive end of the base voltage battery. And some of them move out of the base the base pin, but a lot of them stay in this P semiconductor region. And then when you have the base voltage less than the collector voltage, generally this collector battery is a lot more than the base battery. When that happens, these electrons that are inside of the P type semiconductor are now attracted to the positive end of the collector voltage. And because of that, you're generating a lot of current. So that's the reason why, by varying the amount of voltage that is attached to the base, we can actually vary the amount of current and generate a lot of current coming out of the collector. Awesome. And here is a video that you guys are more than welcome to watch afterwards. It's a really in-depth video that gives you a basic understanding of how BJTs work. And we don't have to watch it though. Awesome. So I know that was a lot. Does anyone have any questions or concerns? I'm more than happy to go over anything. I know a lot of this information you won't necessarily need for ops, but it is going to be going over in ECE2 and a lot of other upper division EE courses. So I figured I'd give you guys a basic rundown of how it works, because when I first saw it, I was so lost and confused and definitely needed a lot of time to understand it.
Yeah, and no worries if you guys don't understand it yet. Obviously, this is just an introduction. Hopefully, just even hearing that and you don't understand it once, maybe next time you hear it and learn about it, it will make even more sense. So, yeah.
Awesome. So I guess we can move on then, if there are no questions. So now that we understand the applications, what they look like and how they work, let's figure out how to use them in circuits. Now, our circuit diagram here, as we discussed, there are two different types of BJT transistors. We have the NPN and then also the PNP. Now you can think of the NPN as the arrow not pointing in to the base. So this is what the symbol looks like. And generally the current runs from the collector to the emitter, and the arrow kind of points in the direction that the current flows in. On the flip side, the PNP is basically just a flipped over, it's always reversed from the NPN. And so the arrow is going in and current runs from the emitter through the collector. So there are a couple of regions of operation that a transistor works in, and this is why the transistor is so important in real-world application, because it has different applications depending on what type of voltage you apply to it. So when our base voltage is greater than both the collector and the emitter, we're creating a short circuit. And basically the current can flow easily from the collector to the emitter. Meanwhile, we have and that's referred to as the saturation region. Meanwhile, we have the cutoff region, and this is when the base voltage is less than both the collector and the emitter. And basically, no current can run through here, and the collector and emitter are, it's like an open circuit. The last region of operation that's really important is when the base voltage is greater than the emitter but less than the collector. Similar to what I was talking about before, this is when you get some sort of amplification of the amount of voltage that you were inputting, which is the base voltage. So let's go ahead and visualize this. I know it's kind of confusing, but you can essentially think of transistors as electron valves with the base acting as a gate to control the amount of flow. So in the saturation region, water is able to flow completely unblocked. In the cutoff region, water is unable to flow because you have the gate blocking it. Meanwhile, in the active region, water is able to flow, but in a controlled manner. So this is when you can amplify things or decrease things. So this is more of a visual representation of what is going on when you use a transistor. And then this slide, it basically gives you, it kind of verbalized what I was talking about. You don't have to worry about the reverse active region at all, but essentially depending on the voltage across the base, the transistor does different things, either acting as a switch on and off or amplifying things. Okay.
And so now that we've gotten through all of the transistor stuff, let's get into IR sensors. And so, but first, before we can get into IR sensors, we have to talk about phototransistors. So we just learned about transistors, which basically have 3 pins, and that you're all incorporating into the system. But the difference with the phototransistor from a normal transistor is that instead of having a base pin, the base pin is basically controlled by the response to the light that is getting sent in. So sort of like a photoresistor, but it has opposite behavior. So the base absorbs light and controls the amount of current that's flowing in. And so when you get light, you're going to have unblocked current flow from the collector to the emitter. But when you get no light, you have less current flow. And also we have a question. Is this NPN or PNP? Can anyone know? Okay, nice. NPM. Okay, great job. You guys are keeping up. Okay. So now that we've learned about phototransistors, let's get into IR emitter and receiver. So basically, IR emitters and receivers allow us to both send IR light and receive IR light in order to do communication purposes in our circuit. So if you see on the right here, we have an IR phototransistor and an IR LED. And so this is the pair that we're talking about, which will allow us to do cool things. And of course, IR light is referring to infrared light. So if you look in the bottom left, you have the spectrum of light, you have visible light, and then ultraviolet on the left side, and then infrared is on the right side. So yeah, basically just a spectrum of light that we can't see, but this hardware can see. And so yeah, basically we use an LED which produces the IR light, the IR LED or the IR emitter, and then a IR phototransistor, which then receives that light. And using these two together will allow us to make really cool things. And one big example of that is a distance sensor. So the IR emitter is emitting the light, and then it's reflecting on the object in front of it. And then the phototransistor will then be able to detect whether or not light is being reflected back, as you can see in the little diagram there. So if it doesn't detect any light being reflected back, then it knows there's nothing there. And then if there is something being reflected back, it knows based on the intensity of the light that's being reflected back, how close something is. And yeah, that's really helpful for us and for distance sensors. So an IR receiver, this is what the parts will actually look like in the circuits that we use, at least. Sometimes they look a little bit different, but these are the forms that we're going to use. So the IR receiver is dark, and the shorter lead is positive with a round edge. And the IR emitter is clear, and it looks like a white LED, and the longer lead is positive with a flat edge. Okay. And now, a short aside from IR emitters and IR receivers, we're actually going to talk a little bit more about coding. Yeah. So we're going to talk about for and while loops. So when we're coding, we don't want to repeat the same thing over and over again because we're programmers, we're lazy. We don't want to do the same thing over and over again. So instead, we decided to use things like for and while loops, which will repeat the same code over and over again, given a condition. So we have the two examples here and what they look like. In the while loop, we start off with while, and then we give it a condition, and then we do open and close curly brackets. And then whatever code is inside of those curly brackets gets done repeatedly as long as the condition is true. So basically, it will start off, read the condition. If the condition's true, it'll run through the code, and then it will go back, check if the condition is true again, and then just repeat that over and over again until the condition is false. For the for loop, it's pretty similar, but instead of just checking for the condition, basically it checks for the condition like in 3 parts. You have initial, and then your condition, and then increment. So basically what those 3 different parts of the for loop do is that initial is just something that runs only the first time that you get to the for loop. So basically you want to use it for setting up a variable that will then be used as the condition. which I'll show later. But yeah, it only gets run once, and then the condition gets run each time to check whether or not you should keep looping through the for loop. And then the increment is a statement that also gets run each time, and it's what you want to use to change the value that's actually being checked in the condition, so that at some point the condition no longer is true, and so the for loop will eventually end. But let's start with a while loop example. So say I wanted to use this code. I wanted to just printed 1, printed 2, printed 3. You know, in the real world, you're not going to really want to do this, but say you wanted to. Instead of doing that, we could just use a while loop. And so we start by making some sort of variable. We have int I equals 1 here. And then we give that as the condition into the while loop. We say while I is less than 6, print printed, and then do a print line of I, which is the number that we gave it. And then at the end, we say I++, which if you haven't seen this before, means I equals I plus 1. And so the while loop will then just keep going. I will keep getting bigger until it finally gets to 6. And so it is no longer less than 6, and it won't print anymore. So it will have the exact same output as the code above, but just in a format that makes more sense to our brains, and it definitely looks a lot better. So you don't have to rewrite the same code over and over again. Okay. And now, one reason why you might want to use a while loop, especially while you might want to use it over a for loop, sometimes you might want to write an infinite loop. So in this case, you would just do while true, and you can make it run infinitely, or until your computer stops, I guess. But yeah, it'll just go literally forever, which can be helpful in certain cases, especially in like Arduino style projects, where sometimes, like, since the loop function in Arduino goes forever, sometimes you just don't want it. You just sort of want the program to end. So sometimes I would just put like a while true loop there to make sure no other code is running. But yeah, sometimes this can be helpful. But now a for loop is really similar to a while loop, but instead we have more statements in the condition checking, basically. So just like before, we have integer I equals 0, and then I less than 6, I++. So basically we all saw these things in the other previous example, but this time it's just a little bit nicer to use the for loop, because we can put a bunch of those things just all inside that parenthesis statement at the beginning, rather than writing them inside the actual while loop. This code is a little bit wrong, I'm noticing now. It should say I equals 1 to get the exact output of above, but you get the idea. And yeah, that is for loop and while loop. So does anybody have any questions about those before we get back to a little bit more about IR transmitter receivers? Does that make sense, everyone? Okay, great. Going to move on. So back to IR sensors. So IR sensors can oftentimes have a lot of noise. This is especially due to sunlight, which transmits light in the IR spectrum, and that we can't see. So different light conditions in a room will cause a lot of problems for IR emitter receiver circuits that we like to build, because it will never have the same like 0 value, basically. We'll never know what value it gets just when we're not shining any light on it. And so in order to fix this, we want to calibrate the sensors at the beginning of our code whenever we use them, in order to get what the value of, basically to get what the 0 is for any given light condition. And we can do that using code, using something that we just learned, which is a for loop. So this is the example of code that we would want to do to help calibrate our IR emitter and receiver circuit. We want to make a variable called 0, and then basically we loop through 100 times, just basically 100. It doesn't matter the actual number, but we just want something really big. We just want to loop through it a bunch of times, and then each time record what the IR emitter was receiving at that time, or what the IR receiver was receiving at that time, when you're not shining anything on it. And then from that, we just take the average of that by dividing by 100 again, and that will give us a value that is the average that it's getting just in whatever your light condition is. And so this will essentially calibrate it so that then we get conditions that will act the same every time, because the 0 is just corresponds to exactly when it's not receiving anything. And yeah, that will be really helpful for our project. So this so this will be really helpful for the capstone and for an optional project that we're doing. But yeah, that's basically what I wanted to talk about IR emitters and receivers. And so yeah, I think that's pretty much it for the lecture.
Thanks for coming out, you guys.
Yes, thanks for coming, everyone. Does anyone have any more questions about anything before we go?
Okay, I'm going to stop.